Hi everybody, I'm Kevin Vermeulen, third year PhD student at Sorbonne University under the supervision of Olivier, Fourmaux and Timur Friedman. And today I'm going to present a joint work with Professor Reza Rejaie at the University of Oregon. And we present today limited, a new alias resolution technique based on ICMP rate limiting. What are those traces? Those traces correspond to 10 different routers responding and non-responding to ICMP echo request, or ping. Black strokes correspond to responses and white strokes correspond to non-response. Why aren't they responding all the time? Because these routers are under ICMP rate limiting. What is the relationship with alias resolution? Well, if you look at those traces, it shows 5 pairs of alias interfaces probed while the router is under ICMP rate limiting. And you can see that there is a shared behavior between each pair of aliases. We present limited today that leverage this observation that ICMP rate limiting is shared between the interfaces of a router to build a new alias resolution technique. So our contributions are limited, which is a new alias resolution technique that extends the spectrum of routers that can be tested for alias resolution. Namely, it greatly improved the coverage for IPv6 and it complements the existing technique in IPv4. And we also provide the first technique that leverages ICMP rate limiting for alias resolution. And we also provide all our code, which we make it available to the community. ICMP rate limiting is a very simple concept. So let's suppose you have a vantage point VP and you have an interface A on a router. And if you send an ICMP echo request to this interface, what you will basically receive is an ICMP echo reply, right? And if you start ramping on the probing rate, you will send, for example, 128 packets per second. You will receive 128 packets per second from the router. And the thing is that let's assume that this router has ICMP rate limiting configured to 500 packets per second. So what will happen if you are sending more than 500 packets per second, for example, 1000 packets per second, you will not receive 1000 packets per second, but you will only receive 500 packets per second. So you will observe losses. And those losses are because of the ICMP rate limiting. So as a short recap, ICMP rate limiting is a feature on the routers that limits the number of ICMP packets sent by the router. And at first, it was designed to prevent DDoS attack. And it has a very nice property for our technique, alias resolution, to be mandatory in IPv6. So now that I've described ICMP rate limiting concepts, let's first step back and have a look on what is the current state of the art in alias resolution. So alias resolution has been widely studied by the community, and it has a lot of contributions in it. And the question is really, is it really possible to make a contribution in this area, given all of the work that has been done, both for IPv4 and IPv6? So before starting our work on alias resolution, what we've done is that we've looked if there was still room for improvement in this area. And we've came up with a taxonomy of the different alias resolution techniques. So the first class is signature. So signature means that you're sending a particular types of packets and you are waiting for responses that forms a particular signature to infer that IP addresses are in fact aliases. So for example, you send packets to 2 different interfaces and the response comes from the same source IP address. That's a Mercator paper. Then also there is some IPID based techniques. So here basically you send packets to the router and you form IPID time series and you compare if they are monotonically increasing together. And if that's the case, there is a high probability that the IP addresses are aliases. There is also its cousin in IPv6, which is based on the IP fragmentation identifier, which is a speed trap paper. Also, you could use IP options, like timestamp option used by Pythia in order to trigger a particular signature. Another thought of alias solution techniques is based on topology analysis. So basically here you have an input set of measurement that you can convert into a topology, and then based on topology feeder, you infer that some interfaces must be aliases. So that's the work made in the APAR paper and the KPAR evolution of this work. And also you could use like record raw option. This is a work done by Discarded. There are also other types of alias solution techniques. For example, using the reverse DNS. So if there are a lot of similarity between the DNS names, some IP interfaces are likely to be aliases. And to see if there was still room for improvement, we've applied a very simple filter to these different techniques. We've just filtered the ones that had a tool available. And the result was striking, because we only obtained 3 tools that were available, namely MIDAR and the SpeedTrap and KPAR. And the thing is that if you further filter by only taking the tool that are doing high precision, you have only 2 tools that are available to the community, namely MIDAR and SpeedTrap. So there is definitely room for improvement here, because these 2 tools have limitations. First of all, MIDAR in IPv4 is based on IP-ID, and that has been shown to be a potential vulnerability for fingerprinting. And SpeedTrap is not applicable to Juniper routers. So here we present limited, which both works in IPv4 and IPv6. And it leverages the ICMP rate limiting signature, which is independent of IP-ID. And it also works on Juniper routers for IPv4 and IPv6. So now that I have described the state of the art and the current limitation of the state of the art, let's have a closer look of how we've designed limited. So limited as an alias solution technique takes as input a set of IP addresses and outputs a set of alias sets. And again, the key idea is to leverage the fact that ICMP rate limiting is shared by IP interfaces of a router. Meaning that, let's have a look on this configuration. So here we have VP, or vantage point, and a router and 2 interfaces, A and B, and the router has an ICMP rate of 500 packets per second. And for example, let's suppose that we send 600 packets per second on A, so that the router will be rate limited. And we send 20 packets per second on B. Let's see what we observe. So what we'll observe actually is that we will have both losses from A and from B. And that is a signature that limited leveraged in order to classify A and B as aliases. So let's have a closer look on how the algorithm works. So first of all, select one interface A from the input set. And the goal first is to find the probing rate that will trigger ICMP rate limiting on A. So we will try to find a loss rate, lambda, within the target loss rate interval, which is alpha and beta. So here the setup is the same as we had before, except that we have added the target loss rate interval informations in the top left corner. So we start by sending 64 packets per second because it is a threshold where we have observed that below this threshold we haven't found any router performing ICMP rate limiting in our study. And because we're sending 64 packets per second and the rate limiting is 500 packets per second, what we observe is that there is no loss, so lambda equals 0. And because lambda is lower than alpha, what we're doing is that we're doubling the probing rate. So a rapid calculus brings that you need actually 512 packets per second to start triggering losses from A. And the thing is that you will trigger some losses, but lambda here will be equal to 2.4%, which is below alpha, so we're still doubling the probing rate. And it is only when you arrive at 1024 packets per second that you will trigger a loss rate which is above beta. And because it is above beta, because it is 51.1%, we will start a binary search in order to find the right rate to probe in order to have a lambda which falls within the target loss rate interval. So finally, in fact, the right rate that we were looking for is in fact 544 packets per second, because it triggers a loss rate of lambda equals to 8.1%. So we call this rate for A as triggering rate. And so when we have found this triggering rate, we will probe A with this triggering rate and all of the other interfaces in our input set with a low rate to generate loss traces. So for example, look at this configuration where we have three interfaces, A, B, and C. So we will send packets to A with its triggering rate, namely 544 packets per second, and 20 packets per second on B, and 20 packets per second on C. And what we'll observe is that because the rate limiting is shared between on the router that owns A and B, the behavior that we expect is the following. There will be losses on A and B, but no loss on C. But you will tell me, right, losses could totally occur elsewhere in the network, and that's totally correct. So what we've done to prevent, to make false inferences based on external losses is the following. So we've came up with the concept of control interface. So control interface are obtained for each interface that in our input set. We perform a Paris trace route towards these interfaces, and we save the last, the closest interface from the target interfaces, and we call that control interfaces. And when we're probing, whenever we're probing an interface, a target interface, we also probe its control. So what should it give here is that because D has been found as being the control interface of A and B, we probe A, B, and D together. And if the losses that are occurring on the router that owns A and B are in fact due to ICMP rate limiting, what we'll observe is that there will be losses on A and B, but no loss on D. And we perform that for all of the other interfaces. So here we have a complete view of what happens, and the result of that is that normally there will be losses on A and B and low loss on C, D, and E. So once we have generated those loss traces, the challenge is to classify those loss traces to be able to determine which of those loss traces corresponds to aliases. And if you look at those traces, you see that there is no simple pattern that we could use here. So what we've came with is a solution based on machine learning. So our machine learning technique is a supervised learning technique. So we needed first a labeled data set. So first of all, we've run multipath trace route to some destinations, and we've gathered these numbers of IPv4 and IPv6 addresses. And then we have labeled our data with state-of-the-art tools, so MIDAR and SpeedTrap, because they're known to produce very low false positive. And any alias pair that was discovered by one of these tools was labeled as alias. And for the non-alias label, it was a little more complicated because we have to deal with potential false negatives that these tools have. So what we've done is that we have conservatively taken some pairs of IP addresses that were found at 6 hops away from each other to label them at non-alias. So from this labeling, we obtain at the end a labeled dataset of 2000 IPv4 and 1000 IPv6 alias sets. And so based on the alias pairs and the non-alias pair that we have labeled, we form heterogeneous sets of alias and non-alias IP addresses. And then we run limited limiting against these different heterogeneous sets, and we train the algorithm based on the loss traces generated by limited limited. So the next challenge of our work was to look at those traces and be able to extract some relevant features for our classifier. Let's have a look at the fifth pair of the previous picture. So first of all, we extracted the loss rate from this loss traces. So here, the loss rate is approximately 50%. We also chosen the change point at the feature because here what we have observed is that definitely the two IP interfaces are changing their behavior from responsive to non-responsive at the same time. We also extracted as a feature the transition matrix from this time series. And we also performed the computation of the correlation between those two time series and used it as a feature. So we've run different classifiers, classic classifiers on this data set. And the first thing that we observe is that random forest is performing well in terms of precision, both for IPv4 and IPv6. And it has also the best F1 score if we only take the high precision classifiers in IPv4 and IPv6. So we've chosen random forest for both IPv4 and IPv6 classifiers. So with this random forest classifier, what we're doing is that we have those loss traces. So we input the loss traces features into the classifiers, and then it outputs A and the interfaces that it has inferred as being its aliases. And once we have this new set of aliases, what we're doing is that we pull out A and its aliases from the input set. And then you just repeat the procedure until you have no more interfaces in the input set. So let's have a look on the evaluation now. We've evaluated limited on two ground truth networks, Internet 2 and Switch, and we've compared this performance against MIDAR and SpeedTrap, the two available tools for IPv4 and IPv6 state of the art. So Internet 2 is composed of Juniper routers and Switch is composed of Cisco routers. So there are a couple of observations that follow this table. So first of all, we can notice that limited has a very high precision, and it revealed no false positives on these networks, both for IPv4 and IPv6. And then the second important observation that must be made is that SpeedTrap, as expected, did not reveal any aliases on Internet 2 because Internet 2 is composed of Juniper routers. But limited was able to reveal some aliases from Internet 2 network. And the second thing that we can say is that SpeedTrap and limited are complementary because the transitive closure of the two brings a better recall than the recall of the tool taken separately. Another aspect of the evaluation is the number of packets sent, and there is definitely a trade-off here because limited sends a lot more packets than MIDAR and SpeedTrap. So the evaluation of limited brings two different lessons. The first one is that limited is a high precision technique for alias resolution. The second one is that it opens a new class of routers for alias resolution in IPv6, not solely Juniper routers. It also complements existing techniques for v4 and v6, but there is an inherent trade-off, that is its high overhead. So as future objectives, we definitely want to reduce limited overhead by using pre-clustering techniques to not compare an IP address with all of the others in the input set, but compare them to small cluster. As we've seen in the evaluation, limited sends way more packets than MIDAR and SpeedTrap. And that raises ethical concerns. And there is an entire section in the paper dedicated to ethics. So now I'm going to present the different dispositions that we've taken so that limited has a minimal impact on the routers. So first of all, we have done some joint measurements with operators, and we've asked them why we were running redundant limited on their routers to measure the CPU overhead that the tool was triggering. And so we've done joint measurement with two networks, Switch and SurfNet. So from Switch, which is using Cisco routers, we had no observable changes on two core routers that they had, and on the lightweight router that they were using, they had a 29% overhead. And on SurfNet, which is using Juniper routers, we observed up to 4% of CPU overhead on the module card, which is not the CPU central card, they told us. And for all of these measurements, the measurement lasted for 1 or 2 minutes at most. And the second thing that we have done is that we have done our own experimentation in a lab environment. And we've performed CPU monitoring as well as data plane and control plane monitoring on more than 10 years old routers, to be conservative. And what we have observed is that we had no impact on data plane nor on the control plane. And we had a CPU overhead of maximum 40% during 1 minute or 2 minute measurements. And at the end, what we could say is that we have definitely designed the limited algorithm to trigger minimum of disruption for other measurements. Meaning that we trigger a loss rate, a very low loss rate in the target interval, so that other measurements could still reach the router with a very high probability. So to conclude my talk, what I would say is that limited is a new alias solution technique that extends the spectrum of routers that can be tested for alias solutions. So as we've seen in the evaluation, there is a great improvement in IPv6, and it complements also existing technique in IPv4 and IPv6 as well. And it is the first time that ICMP rate limiting was used to perform alias solutions, so we hope that this idea could be leveraged on future work. And we also make a code available on this address. So I thank you for your attention, and I open to question now.